In this video, I want to start talking about how to analyze contaminant transport. And the topics we're going to cover will be, we'll start with partitioning. That'll give us a basic understanding of how a molecule of contaminant is distributed amongst different phases in the subsurface. And then we'll move on to look at how that contaminant can be transported in flow and how it can disperse in flow and how it might be changed with reaction. But what I want to start with is to look at the process of partitioning. And this is a photomicrograph of some TCE that is dyed here red. And it's in a micro model where this is a grain, a solid grain, and these are pores. And you can see that the TC has been broken up into these small droplets or ganglia. And so what we're thinking about when we're considering partitioning is that in these ganglia there are many molecules of TCE in there, and those molecules are going to get distributed out here in the water. They're going to dissolve in the water, but they may also partition onto the solid phase. And so understanding that distribution is really going to be what we're talking about here with partitioning. So we can see that a little bit more detail with this simple diagram where we've got some solid mineral grains, and then the pore space is filled in part with water and in part with air. And there's also some naple ganglia here in the pore space, and here's some carbon grains. So we recognize that there are a variety of different phases here: air, naple, water, solid. And among the solid, we have the inorganic minerals and the organic grains here that I'm calling a carbon grain. And so the molecules that would be here as in a liquid phase as the naple, I'm drawing them now as these small red dots. So if these are molecules, then we can see that the molecules that form the naple are distributed all through this material. And if we have the concentration in any one of these phases as really a representative of how many molecules are in that phase, then we can take the ratio of the concentrations in these different phases relative to one another. And then we get these arrows here. So the ratio of the contaminant that's in the naple versus air, that'll have one. That's one particular type of partitioning, and these red arrows that I've drawn here are other types of partitioning between these different phases. And so that's what I want to talk about. These are the four main types of partitioning between the naple and the gas. That'll be characterized by the vapor pressure between the dissolved contaminant in water and the gas. That's Henry's law of partitioning. Between naple, a liquid phase, naple, and water, that's solubility. And between contaminants that are sorbed onto a solid phase here and dissolved in water, that's sorption. So let's look at the partitioning between naple and gas first. And I want to call your attention here to, I kind of think of this as a little experiment where this is a vial, this blue box is a vial, and we fill it up partially with some naple here. So that's this liquid, this non-aqueous phase liquid, and we leave a headspace. And so up here in the headspace, there's some molecules that were in the naple, but they go and partition into the headspace where they're vapor. And so then we have a partitioning between the naple and the vapor. If we just let this vial sit and equilibrate, then the concentration of the compounds up in the headspace will equilibrate out. And the way we're going to describe that is using the vapor pressure of the compound that is forming the naple, the vapor pressure in equilibrium with the naple. Now, vapor pressure, what this means is this is the partial pressure due to the particular compound. And the way to think about that is if we have a surface here and there's some gas over here on this side, then the gas has various molecules in it. So these are molecules. And remember, molecules in the gas phase are moving around. They have different velocities and moving around by Brownian motion. And that motion causes some of them to hit this surface, and they're going to bounce off. And that effect there, that kinetic effect, creates a pressure. And on this side, this is a solid. Then there's an opposing force that is counteracting the force caused by the impact of these different molecules that are moving from Brownian motion. Well, if it's air, the air has a lot of nitrogen and oxygen, and it also has some water molecules in it. So there's a water molecule, and it's moving around, and it hits the wall, and there's another one, and so the total pressure that the gas is creating, it's being opposed by this pressure over here, or by this stress here. The total pressure is the sum of the contributions from these different molecules that are moving and impacting the surface by Brownian motion. So if we have just a small fraction of the molecules as a water vapor, then they're contributing just a smaller fraction of the total pressure. And so that's what we mean by the partial pressure. It's a measure of the concentration of the molecule of a particular species in the vapor phase. So an example of that is the vapor pressure, and expressed as a head of water vapor in air, is this. So the pressure head, 135 millimeters of water, which is about 5.3 inches. Now the total pressure, the total atmospheric pressure, is about 10,000 millimeters. It's about 10 meters or 34 feet. So of that total pressure head of 34 feet, about 5.3 inches of it is due to water vapor when the at standard pressure and temperature. Okay, so a small fraction, but still, a measurable fraction. So that's what we mean by vapor pressure. And we can look at the effects of, we can look at the vapor pressures for various different organic compounds. This is one, vinyl chloride, and this has a vapor pressure that's a good bit higher than water. Water is 135, this is 2600. Acetone, it's also greater than water, about double what water is. And then these other ones, benzene and TCE, those also have a vapor pressure that is significant, but it's a good bit less than, well, maybe half or so of what water is. Okay, so these are some examples of the vapor pressure, basically the tendency for the naple to partition into the vapor phase. Okay, so now let's switch our attention to the partitioning between water and gas. And I've got another experiment here where we've got a vial and it's filled partially with water, and we dissolve some compound in the water, and we put that water into the vial, and then we let it equilibrate. And some of these contaminant molecules that are in the water are going to partition into the headspace. And if we let that sit there and equilibrate, there'll be a concentration that is in equilibrium in the headspace and in the water. And so I guess what we can do then is repeat that concentration or repeat that experiment and plot up the results. So here's the vapor pressure or the mass per volume in the gas as a function of the concentration in the water. And what we find is that if we do an experiment where we would put water with different concentrations in this vial and then measure the headspace, that if we start with a low concentration, we get that concentration in the headspace, and we use a higher concentration in the water, and we get a higher concentration in the headspace. And then what we find is that it's roughly linear, the relationship between the concentration of the water and the concentration in the headspace. And this slope then is what we call Henry's constant. And Henry's constant relates the vapor pressure or the concentration of a compound in the gas to the concentration dissolved in water when the gas and the water are in equilibrium. Okay, so Henry's law constant, case of H, it's going to be a measure of concentration in vapor to concentration in water, the measure of this ratio. And this ratio also when it's in equilibrium. So we can take a look then at what kind of units this would generate. So if the vapor concentration is a vapor pressure expressed in atmospheres, and the concentration in the water is moles per liter, then we get a Henry's law constant that has these kind of funny units: atmosphere liters per mole. And that this is a fairly common unit for Henry's law. We can also think of Henry's law, though, as a ratio of moles per liter in the water and in the gas. Now, that's not usually how we measure the concentration in the vapor phase, but we can do it. We can convert and get that concentration. And then if we take the ratio of the moles per liter in gas to the moles per liter in the water, then this is kind of nice because this gives us a dimensionless Henry's law, and we can kind of think of this then as the number of moles of the molecules. If we have equal volumes of water and gas, then this is just directly the ratio of the molecules that are in one phase compared to the other phase. So that, I think, is a little more intuitively appealing. Just conceptually can visualize that a little bit easier than these units. And we can take a look over here on this side of the slide to see some values of kH in this dimensionless form. The kH of CO2 is pretty high. This is getting it's certainly on the certainly closer to one than it's getting pretty high. So this means that there's a higher concentration of CO2 in the vapor phase compared to the water phase when the two are in equilibrium. Here's another comparison. This is oxygen. So there's oxygen in the atmosphere and in the water, and this ratio is given here. So you can see that on a per mole basis, the concentration of the vapor is low compared to the concentration in the water. but still, I mean, and particularly if we compare it to CO2. Um, TC, about 1% by mole, um, and benzene, here it's about a quarter. So this is a good bit higher than these other two. But I guess significantly, this is going to play an important role. This partitioning between the water and the vapor is going to play an important role when we look at remediation, because the gas phase or the vapor phase is going to be a lot more mobile than the water phase. So if we can get the contaminant to partition into the vapor phase, we have the possibility of mobilizing it and moving it. And these values of Henry's constant are large enough so that this becomes an important effect. So that 0.011 for TC is large enough so that this partitioning could be used during remediation. Okay. So another type of partitioning that's going to be important is the partitioning between naple and water, and I'm calling this the solubility. The solubility is going to be an expression of the concentration in water that is in equilibrium with the naple. So we look over here on the left to our little box. We've got some naple in there. We do an experiment where we fill the vial with water, and then we put a couple drops of naple in there. There's the naple, and we let it equilibrate. And then some of these molecules of naple are going to partition into the water and dissolve into the water. We let this go to equilibrium, and then we measure the concentration in the water, and that's going to be the maximum concentration that we can get if the naple still was present. And so this is called the solubility. And I listed here in this table the solubility of some different organic compounds. So here's TC, this very common chlorinated solvent, and here's the solubility of TC in milligrams per liter. So 1100 milligrams per liter. That's about, let me see. So that's about, let me make it a little bit easier to read. So this is about 1 gram per liter. 1.1 gram per liter is the maximum that we can dissolve into water. And if we look at some of these other compounds, PCE, it's a bit less. 1,2-DCA, it's a bit more. Carbon tet, similar. Methylene chloride, good bit more. But in general, what we see is that for a lot of these different compounds, that this value here it's kind of in the ballpark. So 1 gram per liter would be 0.1%. 1 gram per liter is going to be 1 part out of 1,000 on a mass basis. So what I have here in just a summary way is that organic liquids, it's hundreds to thousands. So on a per mass basis, it's 0.01 to 1% is the solubility. So what that means is that importantly, the naple is soluble in water, so we can have molecules that form naple dissolve into water, and so that's important because that means that we have then contaminated water. But importantly, it's a pretty small percent. The maximum concentration that can be created when these compounds are in equilibrium with water is a pretty small percent on a mass basis. And so one of the implications is that if there is some naple in the ground and we're trying to dissolve it, it's going to take a lot of water to dissolve a small amount of naple. So, in this case, in TC, it would take 1,000 liters of water to dissolve 1 liter of TCE um, at the highest concentration that we could get into the water. So dissolving naple in water is going to be a tough way to remove the naple, but but we see that it is going to dissolve into the water. And so then if we look at this next column here on the right, we can see that this is the MCL, and that's the maximum concentration limit, and that is also in the same units of milligrams per liter, and here are those values. So for TCE, it's 0.005 um, parts milligrams per liter. So 0.005, to put that in context, that is well, 1 milligram per liter is 1 part per million. So 0.005 is equal to 1 part per billion. Or I'm sorry, five. I'm sorry, that's not right. Five parts per billion. Okay, so what we get from this is the maximum concentration limit um, is quite small, and many orders of magnitude smaller than the solubility. So over here in this column is the ratio of the solubility to the MCL. And you can see these are pretty big numbers. There's 10 to the fourth, 10 to the fifth, there's 10 to the sixth. And so I guess a way to think about this is that if we start with a liter here of water, um, and if it's TC, then we can put 1,100 milligrams in that liter, and that's it, and that'll reach the solubility limit. But then, if we take that water that's contaminated um, to the maximum concentration that it can take, and if we want to dilute it down to the MCL, so if it's just a bit above, well, if it's at the MCL, it still is considered contaminated. So if we then take this liter and dilute it down by mixing it with clean water, then it's going to be a much larger volume. It still is above the MCL, and this volume is going to be that ratio. So this is going to be 2 times 10 to the fifth liters that are then right at the MCL. So what we get out of this is that these organic compounds, organic contaminants are they do dissolve in water. The solubility is low enough though so that it's going to be hard to dissolve away the contaminants. But when we do that, we're going to create large volumes of water that are potentially above the MCL. So the bottom line with all of this is that because of this solubility effect, naple in the subsurface will create a long-term persistent source because the solubility is pretty low. Um, but well, it'll create a source because the solubility is low. It'll be long term because the solubility is small, but the MCL is much smaller. So it'll create a large volume of contaminated water potentially. So this is really why we have these persistent plumes associated with chlorinated solvent contaminants, particularly when naple is in the ground. Okay, so I want to just refresh your memory about how concentrations are expressed. In water, concentrations are expressed as mass in the water per volume of water, and we've just been seeing that. So milligrams of a contaminant per liter of water, that would be 1 part per million, and that's a common way of describing concentrations in water. But if we have concentrations in soil, then a common way to express that is the concentration of the contaminant in milligrams per kilogram of soil. So the ratio is mass of a contaminant in the water per mass of solid soil, and we get a concentration of milligrams per kilogram. So the reason I want to point this out is because this next partitioning topic is the partitioning between the dissolved contaminants in water and the solid phase of the porous medium. And this will be called sorption. So here's our experiment. We've got some water, and now we have some solid compounds. That would be a solid mineral phase, and then we've got some carbon here that are shown schematically, and then we've got some dissolved compounds, and then here these compounds are sorbed onto the surface of the solid right there. So we do an experiment. We start out with a low concentration of compounds dissolved in water. We add some solid phase. We measure then the concentration that's sorbed to the solid, and we plot it up. So here's our concentration in the water that we start with. We measure the concentration that's sorbed onto the solids, and we plot that point there. And we repeat this. And at low concentrations, the concentration in the water to the concentration of the solid forms this linear plot, and we can fit a straight line to it, and we can get a slope to that, and the slope is called the distribution coefficient. And basically then this is saying that the contaminant on the solids equals the distribution coefficient times the concentration in the water. Okay, so this gives us a way to relate concentration in the water to concentrations on the solids. And KD then has to have the units that allow us to make these units compatible with these units. So one application for KD is in this expression that we saw a couple of classes ago for the retardation coefficient. And when we can express partitioning using KD, which is going to be typically for low concentrations, then we can use this to calculate or at least to estimate what the retardation factor is. I mentioned here that this relationship between the sorbed concentrations and the concentration of water is good in many cases when the concentration is quite low. What happens though is that as the concentration increases, it no longer becomes or no longer stays linear in a lot of cases. Well, essentially in any case that's going to be true, and the reason is because you can think of this like so, that when the absorption process is going on, let's see, here's a solid grain, and that solid grain has places on the surface of it that can accept a contaminant molecule. So here's a contaminant molecule, and when that contaminant molecule is stuck to the surface, there's a particular place, a structure on the surface that accepts that molecule and allows it to to stay there, to bond. There has to be a certain kind of bonding between the solid and this molecule here of contaminant. So you might imagine that on any given contaminant, there are a finite number of places where this bonding could occur. And so at some point, if the concentration out here in the liquid becomes high enough, these sites where the absorption is taking place, they begin to fill up. And at that point, then at some point they might be completely filled, and then we could have more concentration here. We can have more molecules added, and if all these sites are filled, then we can't really absorb any more. So this general concept of having them be proportional works nicely when these sites are only slightly filled. But as we increase the concentration in the water, the sites are going to fill up, and at some point it's going to be harder and harder to find a place for the absorption to occur on the surface of the solids. So to account for this, there are several other isotherms, and I guess I should point out that this plot here that I'm showing, let's see, this plot here, hold on, this plot here, concentration of the solids to concentration of water. This is called in general, this plot is called an isotherm. And if it's linear like this, then it's a linear isotherm. So what I showed you up there was a linear isotherm, but what I'm showing you down here, it's the same axis. So it's concentration of the sorbed versus concentration in water. But what we see here is now it's nonlinear. And so this is a isotherm, but it's a nonlinear isotherm. And this is good for low and high concentrations. There are a variety of different formulas that have been proposed to describe this kind of behavior. Freundlich this says the solid concentration is equal to the dissolved concentration to a power. So if n is 1, then we just have this one here. Langmuir says, no. The solid concentration is a function of the dissolved concentration like this. And now there are these two parameters, alpha and beta, that are used to fit the data. So these are examples of nonlinear isotherms. What we see is if we take this down to low concentrations, down here in this range, that both of these are saying that the concentrations are linearly related, the concentration of water is linearly related to the sorbent concentrations at low concentrations. So both of these will work for this case here, but they also include this effect that happens when you have high concentrations. Now, a lot of times in groundwater, when we're right in the vicinity of of naple, and we're getting we could have some high concentrations there, but for the most part, in plumes, the concentrations are low. So this linear isotherm works pretty well, and we can see that even if we have this kind of nonlinear effect, so long as the concentrations are low, then we can use this linear expression. Okay, so the distribution coefficient, Kd, that's what's describing this absorption effect for the linear isotherm. Now, one way that we could determine this is with an experiment, and indeed experiments are done very much like what I just showed you, where we take a vial and fill it with water of some concentration, and we then put in some soil, and we shake it up, and then we allow the contaminants to partition onto the soil, and we do that multiple times, and we get a plot. Looks like this. We fit a line to it, and we get KD from that. So that's one way to do it, and that's great if you can do that, but that requires some lab work, and it's a good bit of effort. And what's often done then is to estimate KD before you would really get a chance to do this kind of lab work. And one way of estimating it for organic compounds is to recognize that the absorption of organic compounds onto other organic materials, organic solid materials, that's going to be much higher than the absorption between organic compounds that are dissolved and mineral phases. So I guess let me go back a slide, and let me erase over here. So in this experiment, what I had was the light gray is a mineral, and the dark gray is organic carbon. And so you see how I'm showing there are 3 molecules on the carbon and only 1 on the mineral. And that's just a schematic way of indicating that for organic compounds, we're expecting them to prefer to absorb onto other organic materials, organic solids. Expect that to be more important than absorbing onto minerals. And so one of the things that you can do is to measure the fraction of organic material in soil, and this is fraction of organic carbon in soil, or in the organic, or in the aquifer material. So this would be let's just say in the porous media. And we can do that just by separating out the organic material and analyzing it, measuring it. And the beauty of doing this is that this term here, KOC, this is the partitioning between the contaminant that we're interested in and organic carbon. And this has been measured. Organic carbon is pretty uniform, standardized material, and people have measured the partitioning between different organic compounds and organic carbon, and they've compiled that information in tables. And what I'm showing here is one of these tables. And let's see, for benzene, that says log KOC, and then there's KOC. This is calculated, and then here's measured. So log KOC 1.77, actual KOC is 59. So 59 is the KOC, but often what you get in these tables is log KOC. So that's 10 to the 1.77, right? So if you're given a table with log of KOC, make sure to do that to get the actual KOC. And then to get the KD, you would take that number there and multiply by the fraction of organic carbon. In sediments like what we have down at the Clemson Bottoms well field, it would be typical to have several percent of organic carbon in sediments like that. Okay, so this gives us a way to estimate KD just based on knowing what contaminants are there, and then utilizing these tables like this. So that would get us a preliminary estimate. Okay, so we've seen here partitioning between these 4 different phases, and they're governed by different concepts and different terminology. The partitioning between naple and air, we saw that as the vapor pressure. Between water and air, so between water here and the air phase, That was Henry's law. And let's see, between naple and water, so we've got some naple here and water, it's going to create a dissolved phase, and the solubility is what was controlling that. And then what we just saw was partitioning between the contaminants dissolved in water and contaminants sorbed onto the solid. That was this sorption. And for linear sorption, we had Kd, the distribution coefficient.